Ropen Company Limited. Methods to treat urban sewage and industrial wastewater can be divided into physical treatment, chemical treatment, and biological treatment. Chemical treatment adds organic or inorganic coagulants, which increases the concentration of total dissolved solids in the treated water, making it an environmentally harmful method. Biological treatment is more economical, but requires a large plot of land where the microbes need to decompose the contaminants over a long period of time, generating greenhouse gases and foul odor. Physical treatment separates pure water from the contaminants without altering the phase of the contaminants, making the process more environmentally friendly and enabling the water to be reused. The filter is a major type of physical treatment device. As shown in the table, filters are classified into the fixed pore and variable pore filters according to the pore structure, and replacement cartridge filters and membrane filters are classified as fixed pore filters. The disadvantages of fixed pore filters include more waste from the frequent replacement of cartridge filters. Membrane filters require frequent chemical cleaning due to the surface fouling that accumulates during the process, resulting in chemical wastewater. Ultimately, the filter must be replaced due to the plugging of the surface pores. Variable pore filters include the traditional multi-layer sand filter that has been used to treat water and the variable pore microfilter by our company. Multi-layer sand filters treat water by backwashing through the medium with only water and air. Due to the easy operation and affordable cost, this treatment has been used in water treatment plants for a long time, but has its limitations as the filtration performance is limited to approximately 25 microns. As the latest water treatment technologies focus on reuse and advanced treatment, this filtration method has been steadily declining. The Vpmf by our company is a fine, long fiber filter that can filter up to 0.2 microns, a significant difference compared to multi-layer sand filters, and has a long lifespan of about 10 years as it requires only water and air for backwashing and regeneration of the filter medium. When looking back on the development of fixed pore and variable pore filters, the first fixed-type filters were mainly made of filters shaped like fabric, cloth, or mesh nets, and the size of the pores was only 50 microns. After the appearance of second-generation fixed pore filters using a porous polymer membrane as the filter medium, technology advanced at a rapid pace, bringing filters such as reverse osmosis membranes, ultrafiltration, and microfiltration, which have been wisely used for ultra-pure water, seawater desalinization, wastewater recycling, and the filtration of drinking water. However, the second-generation fixed-pore filters used a cross-flow filtration technique, which resulted in a low recovery rate of 70 to 90%, along with major maintenance issues such as plugging and fouling. Accordingly, the third generation of fixed-pore membranes has been enhanced with improved backwashing efficiency through flexible hollow fiber membranes. The first generation of variable pore filters includes sand filters, using sand as the filter medium, and multi-layer filters using sand and gravel. The filters have excellent backwashing efficiency due to the fixed pore structure and are capable of filtering particles of about 25 microns. As such, they are still used today. To improve the filtration performance of these filters, the size of the sand medium needs to be smaller. The second-generation variable pore filter forms a filter layer by coating powder around a perforated tube, leading to the development of the technology to dispose of the filter medium with the contaminants through backwashing. However, when the raw water's concentration of total suspended solids is too high, pre-coated filters can shut down due to frequent backwashing and produce more wastewater. The structure of the third-generation variable pore filters combines the advantages of the first-generation and second-generation filters. Fine, long fibers with a thickness as small as 1 to 100 of sand filters are used as the filtration method. Both ends of the fiber are combined with a plastic holder to mount it within the housing. This effectively blocks the outflow of the filter medium that occurs during backwashing, and the fibers are compressed by the pressure of the raw water, creating the filter layers. As a result, the filter can filter up to 0.2 microns with excellent backwashing efficiency. However, a major issue of fixed-pore membrane filters is gel fouling, which occurs when the suspended solids and colloidal particles coat the surface over the filtration process. This leads to increased differential filtration pressure, which also reduces the rate of flow. When operated over a long period of time, contaminants that are similar in size to the filter's pores begin plugging the filter medium. The flow rate versus the operating time curve shows that the flow rate decreases due to gel fouling and plugging that occurs in the filter. The red flow rate curve represents the decreasing flow rate due to plugging, and the prolonged operating time leads to a decrease in the replacement lifespan. The black jagged flow rate curve above the red curve represents the temporary recovery of the flow rate that occurs when the gel fouling is treated with chemical cleaning. This is a typical graph representing most fixed-pore membrane filters. The table represents an extreme dataset obtained from pilot experiments conducted in Korea and Japan. Particles that have a similar size as fixed pores are called SPAPOs. When the raw water contains a large amount of SPAPOs, severe plugging will occur for pore-tight filters, and especially on the separator, plugging all pores within 2 to 3 days. If the SPAPOs consist of strong particles such as sand, silica, or titanium oxide, it will be difficult to recover the filter even with strong acid or strong alkaline chemical cleaners. The wastewater from this is estimated to be about 30 to 40%, which is assumed to be similar to the failure rate of fixed-pore filters. To develop a variable pore-type filter with the advantages of a multi-layer sand filter and the excellent filtration performance for the pre-coated filter, we used an ultrafine filament with a diameter similar to the diameter of the coating powder for the pre-coated filter as the filter medium. To prevent the leakage of the filter during backwashing, each end of the ultrafine filament is fixed with plastic holders. In the Vpmf, as shown in the figure on the left, the inflow of raw water presses the ultrafine fiber filter to the lower part of the housing during filtration, forming a filtration layer around the porous permeation tube at the center. This fibrous filter layer acts as a microfilter cartridge in fixed-pore filters. After the filter operates for some time, contaminants will accumulate on the filter layer and increase the differential pressure. Then, the fiber filter will be dismembered by the backwash that is injected into the treated water pipe, floating within the housing. When backwashing air is injected at this time, the fabric medium will roll in different directions, cleaning the contaminated fabric filter medium through the shearing force that is generated by the water and air. Since the fiber filter medium is made of only weft yarn, it takes less time to wash it perfectly clean compared to general fibers. This method of cleaning is similar to the principle of air bubble washing machines. Cleaning, the filter medium is again compressed by the pressure of the raw water, and the Vpmf repeats this process to filter the water. This video shows the Vpmf infiltration mode. The filtered water before the fiber medium is compressed is called the initial treated water, which is then returned to the raw water tank. This video shows the Vpmf backwash using an artificial sample. The contaminants attached to the fiber filter are separated as the compressed fiber layer is dismantled, which is why the filters with this structure are excellent in terms of the backwash recovery rate. This is the process flow chart of the Vpmf. This is the table of applications of the Vpmf. Portable water plant. A typical water treatment process uses river water as the raw water which is passed through the flocculation tank, sedimentation tank, and filtration tank, disinfected with chlorine, and then supplied to consumers. The flocculation tank coagulates and coarsens the matter substances and turbid matter contained in the raw water through a coagulant, and the coarsened flocculant in the sedimentation tank is separated from clean water by gravity. The small amount of flocculant remaining in the tank is removed through a sand filter in the filtration tank, disinfected, and then supplied to consumers. The current water treatment process has several disadvantages. First, it is difficult to maintain an optimal coagulation state when raw water with low turbidity is injected. An excessive amount of coagulant can be administered on-site, which lowers the water quality, thus requiring powdered activated carbon later down the process. Second, the large size of the sedimentation tank takes up a large area of the water purification plant. This is a disadvantage for emergency water purification systems or portable systems and becomes a cost burden for urban areas with higher land prices. We would like to propose a process combining our Vpmf as an alternative to the existing water treatment process. The turbidity of river water can fluctuate from 5 to 1,000 NTU, depending on rainfall or drought. The Vpmf process can be composed of 3 stages according to the maximum turbidity of the incoming raw water. The first Vpmf process can be applied when the maximum turbidity of the raw water is less than 80 NTU, less than 350 NTU for the second Vpmf process, and less than 1,000 NTU for the third Vpmf process. The backwash wastewater of the Vpmf is physically backwashed, meaning that it can be returned to the river. If the backwater wastewater needs more treatment, it can be concentrated into a slurry using our submerged variable pore filtration, which can be dehydrated and disposed. The recovery rate of the Vpmf process is about 97 to 99% and requires a smaller area that is 1/20th of existing water purification plants. This table compares the existing water treatment process and the Vpmf water treatment process. In comparison, the Vpmf treatment takes up only 1/20th of the area, has an operating cost that is 56% of the existing treatment, and does not require slurring treatment. Moreover, the existing process requires additional costs to operate various measuring instruments to meet the optimal flocculation conditions and more people for operation. Wastewater. When the raw water is injected directly in reverse osmosis systems used in wastewater recycling and seawater desalinization, severe membrane contamination occurs due to the suspended solids and colloids, requiring frequent chemical cleaning. As such, the RO separator needs pre-treatment, which is conventionally done through sand filtration and activated carbon filtration. However, when using these pre-treatment methods, it is difficult to achieve the recommended RO pre-treatment standards of a turbidity, which is less than 1 NTU and less than SDI3. The Vpmf can replace sand filtration and activated carbon filtration, satisfy the pre-treatment standards, and optimize the performance of RO used in wastewater recycling and seawater desalination. The sand filtration or multi-layer filtration systems in existing water, sewage, and wastewater treatment plants generate a lot of wastewater from backwashing. The conventional treatments for backwash wastewater are returning the wastewater to the wastewater treatment plant, coagulation, and concentration. Backwash wastewater is known to account for approximately 10% of treated water, and 95% of this can be recovered by direct filtration through the Vpmf. Since the water quality is equal to or better than that of sand filtration treated water, the results can be used in combination with sand filtration treated water or as backwash wastewater for sand filtration, increasing the recycling rate of water. Ropen Company Limited.